Hey again, welcome to another video. In this video, we're going to take a side step. So I know we've been talking about modeling populations, and we certainly will talk about more modeling in the next video. But the next video has a lot of partial fractions in it. And so what I'm going to do is kind of an optional video for you. If you are very comfortable with partial fractions, great, just go on, take care of another video. But if you need a refresher, and you're not used to seeing partial fractions and differential equations, like sometimes we just get away from those, we don't see them very often. I'm doing this video for that reason, to get us comfortable with partial fractions in differential equations, some algebraic techniques that can help us, like moving some negatives around, that make things just slightly easier. So I'm going to show you my techniques on how to do that. I'll show you some shortcuts when dealing with linear factors, which we mostly get in these population models. And then we'll move on. So if you want to maybe just practice with me, make sure that we still understand partial fractions, how to deal with some negatives and some exponentials that come up. So this is going to be as quick as I can make it, going through 3 examples, just the bare bones on how we go through partial fractions again. So kind of a refresher on partial fractions and differential equations. So let's suppose we have a differential equation. We have, well, dx dt, so dependent variable x, independent variable t, equals x minus x squared, and then x of 0 equals 2. So we got some initial condition on it. What I want you to remember is that these are going to be separable, but when we separate them, they're not going to create some integrals that are very easy or very nice. They're going to create integrals that you need to deal with partial fractions. And so sometimes setting these up, it's very nice to put things in order and factor so your first term is positive. So what we're going to do before we even start is set this up like dx dt equals negative x squared plus x, and factor out a negative x. So x minus 1, let's make sure. Negative x squared plus x looks really good. After we do that, we're going to see that this is a separable differential equation. Could you have seen that right here? Yes, because x is your dependent variable and t is your independent variable. You can group your x as dx and constants dt, but sometimes that negative screws us up a little bit. Not that it's any different. I mean, you could totally do this that way, get everything on one side right now and keep a constant on the right. That's fine, but going through it, sometimes we get some sign errors. Now, is it a big deal? No. And in fact, as we move forward with this, I'm going to be factoring out a negative again and multiplying both sides by a negative. But I've seen a lot of students, when they're just forgotten some partial fractions, really make a lot of sign errors, and that screws up everything. So I'm going to do it this way. You can choose your own way to go on this one, but what I'm going to do is I'm going to move my x is dx, so 1 over x times x minus 1 dx equals negative dt. And when we integrate that, when we get ready to integrate that, we're going to see that on the left-hand side, this is set up really nicely to do a partial fraction. That's why I'm factoring first here instead of putting everything on one side and trying to struggle through it. So I'm factoring, saying, okay, I see that those are some linear factors. That's going to be partial fractions. Now, we're going to spend some time right now to talk about how you do partial fractions. I know you've seen it, but it's might have been a long time. So how partial fractions work? It says you're going to take this fraction, and we're going to understand that we could write this as a sum of 2 different fractions. And here's how you set this up. For every factor, you are going to get a fraction. So 2 factors, 2 fractions. And then for every numerator, you have a degree lower than your denominator. So if we have a linear denominator, you're going to have a constant. If it had been a quadratic denominator, you would have had a linear numerator. So fractions equal factors. Factor equals fractions. And when we have linear factors, you're going to have constant numerators. And then the whole process is really just finding a common denominator. It's not magic. What this says is, if I get a common denominator, my denominators equal my denominators, then my numerators would have to be equal. So the whole process is really just find a common denominator. Multiply this fraction by x minus 1. Multiply this fraction by x. And then if you had found the common denominator, your numerator would be this, your other numerator is 1, and because your denominators are equal, and you found a common denominator, put this together, your numerators would also have to be equal. And then, so moving forward past that, What's very nice about our linears is that you can oftentimes plug in a number like 0 to make one term 0, solve for the other coefficient, or 1, make this term 0, solve for this coefficient. That's really nice with linears. So it's a nice little trick that we do here. We'll say, what if x is 0? If x is 0, then this would still be 1. 0 minus 1. A times negative 1. So 0 minus 1 is negative 1. Plus this whole term would be 0. And it allows you to solve for a very nicely. A would be negative 1. Now, what if x were 1? Well, if x were 1, then this would still be 1. This whole term would be 0. And this would be just b. And b would equal 1. And what that does for us, it says, the one time through, maybe put it in order. Factor, so you see that you got a couple linear factors here. You go, okay, when I make a separable differential equation out of this, I know that I'm going to have partial fractions. It happens a lot in the next video. So we have some partial fractions. We know that we're basically just finding the common denominator and setting our numerators equal. Then we plug in a number that's going to create a term equals 0, solve for the other coefficient. So we've done that and it says you can now rewrite this fraction. You can rewrite this as negative 1 over x plus 1 over x minus 1. We're going to do that right now. So a was negative 1, got it, over x. B was 1 over x minus 1. Oh, I'm not going to have to factor in negative elements. Dx equals integral of negative 1 dt. So on the left-hand side's really nice. We just have a basic integral. On the right-hand side, even nicer, we're going to get negative t plus some sort of a constant. Now think through what's going to happen. We're going to get a couple natural logarithms. We're going to be putting that together. Do you remember that when you have logarithms added or subtracted, you can combine them? And so on the left-hand side, we are going to combine that. On the right-hand side, we're going to put a c sub 1 because eventually we're going to have to get rid of that logarithm. That's going to be an exponential. And so when we have that c sub 1, we're going to wrap that up as e to the c sub 1, probably a plus and minus to deal with an absolute value, and that whole thing is going to be another arbitrary constant. So we're going to do that most of the time with these partial fractions. On the left-hand side, hey, that's going to be negative ln absolute value of x plus ln absolute value of x minus 1. There's not really any necessary use of. We have something very basic. And this is what I was just talking about. When you have two logarithms being added or subtracted, the positive or the plus goes on our numerator, so x minus 1. And this thing being subtracted creates this quotient inside one logarithm where we have the numerator from our positive or plus ln, and the negative gives us our denominator. That minus ln x gives us x on the denominator. Equals negative t plus c sub 1. And this is looking pretty good. Now we can take an exponential on both sides. So here and here, yes, we're going to get absolute value of x minus 1 over x. Cool deal. On the right-hand side, e to the negative t times e to the c sub 1. Do you remember that? How when we take an exponential to this entire function over there, we have e to the negative t, but times e to the c sub 1. Well, if we wrap up this absolute value as a plus and minus, then this whole thing, we've done this many times, we can define that to be, looks like an e, sorry, to be a c. So that's our constant. So x minus 1 over x equals c e to the negative t. Now pause. I know that you want to solve for x. I do too. We're going to solve for x. But do you remember that with these logarithms, that we take an exponential on both sides, we wrap up that whole c to the 1, e to the c sub 1 plus or minus with a c. Right now is a really good time to plug in an initial value or initial condition or whatever they've given you. Because if we start solving for x, we're going to have to eventually solve for c. And it's going to take us a lot of work to undo what we just did. So if we take this x of 0 equals 2, that means that t, our independent variable, is 0 and x is 2. This is much nicer to solve because if you plug in 0 here, this whole thing's going to be 1. That's going to give you c equals 2 minus 1 over 2. That's a lot nicer than having to solve for x and then plug that in and having to resolve for c. That's crazy. So when you're going through these, plug in c basically as soon as you can. As soon as you have a nice arbitrary constant. Not here so much, not there for sure, because that's garbage, right? That's nasty. But as soon as you redefine your arbitrary constant, now's the time. So 2 minus 1 over 2 equals c times e to the 0, or 1. This is going to say that c is 1/2. Now we plug that in right here. So x minus 1 over x looks pretty good. Then we're going to have 1/2 e to the negative t. This is where we want to solve for x. Now I mentioned something a while ago. I said I might have factored out a negative. Here's when I would do that. So I'm trying to explain this. Not that you have to, okay? I'm trying to explain the Leonard way of doing this. What I'm always looking for when I'm going through these integrals, partial fractions, is I'm really trying to make sure that my negative fraction has only one term, if possible. If not, then okay. But I'm trying to make sure that has only one term. Why? Because if that's going to be a natural logarithm and that's going to be a natural logarithm, I want the single term to end up on the denominator. Because I know we're going to be doing an exponential, I know we're going to be multiplying to get rid of that denominator. If this has two terms, you'd have to multiply it, distribute it, subtract it, factor it, divide it. Here, because we only have one time, we will multiply it, subtract it, factor it, divide it. So it saves us one step. Is it really important? It's not. And I'm going to show you in the last example that if we do it differently and have this reversed, it's not a huge deal, but you will have to distribute, subtract, it'll add an extra step there. So one time, just to make sure that we're golden on this, a lot of times we're getting some partial fractions. That happens when we have a constant divided, typically you don't have to have a constant, but here it's going to be constant divided by some linear factors. So we factor, we see that, we do our partial fractions, we're basically doing a common denominator, we're setting our numerators equal, it's going to solve for those coefficients, we're separating fractions, and we're going to get a lot of natural logarithms. Try if you want to, try if you can, to make sure that your negative logarithm has one term. That's really helpful. So we group them as one logarithm, we exponential both sides, we get rid of that, we wrap up our arbitrary constant as a plus and minus e to the c sub 1 equals c, and right there we plug in our initial value problem. That lets us solve for our c, and then we're pretty much good to go. We're going to multiply both sides by x. We're going to group our x's on one side and our constants on the other. So we're going to be adding 1 and subtracting this term. And then we're going to factor x. We're going to factor x because we grouped all the terms that have x in them on one side on purpose so that we could factor and then divide. And so we're going to divide this. And you go, that doesn't look that great. We got some complex fractions. We have a negative exponent up there. So we're going to do a couple things to make this maybe a little bit nicer. Number one, we might choose to multiply both the numerator and denominator by 2. So if we multiply by 2, well, it's going to distribute, but it's going to kill off that 1/2. That'll be pretty nice. So x is a function of t. We'd have 2 over 2 minus e to the negative t. That's perfectly appropriate. That is fine. But you might also see this. You might see some textbooks, some people say, yeah, I'd really prefer not to have that e to the negative t here. So because that's technically a complex fraction, you do have 1 over e to the t. We can multiply by e to the positive t and get our function of x with respect in terms of t would be 2e to the t over, remember, you'd still distribute here, 2e to the t minus 1. E to the negative t times e to the positive t would be 1. You get e to the 0, e to the 0 is 1. So you might get a, notice how they look completely different, right? I mean, they look very, very different, but they are the same exact thing. So that's about all I want to do on this problem. We've used our initial value problem. We've done some partial fractions. This is how a lot of these next differential equations for population modeling is going to work. It's going to say, hey, you have some linear factors. It's still separable, but you have some linear factors under a constant. That's some partial fractions. So make sure you're seeing partial fractions. Try this to get your term on your denominator to be a single, sorry, the negative ln to be a single term, so your denominator is a single term. It does help a little bit, just makes it so that right here, when you multiply, you don't have to distribute. Again, it's not a big deal, it's just a deal. Other than that, we're solving this like normal, and then we're typically wrapping this up. If we can avoid negative exponents, we try to avoid negative exponents. There's two more. I'm going to come back up here and do a couple more just to get us really, really good at this. Hope it's making sense. I hope this is refreshing your memory. Let's try another one. So we're going to start here, another differential equation that says, well, I got a quadratic. That's not going to be partial fractions, right? Because that's like a trig, that's like a tan inverse. No, or sine inverse. Not really. That right there, maybe be more appropriate to write this in a good order. Now, what's going to happen? I'm going to write this as negative x squared plus 1. We're going to factor out the negative, and then we're going to see a difference of squares. But when I do that, when I leave the negative on the right-hand side, I am going to factor a negative from what we get. So I will be changing it back. If you can see that this is 1 minus x times 1 plus x and be fine with it and do your partial fraction from there, great, do it. But over the last 14 years, man, I've seen a lot of students mess that up. Firstly, not see it, and secondly, mess this up with some sign errors and get the wrong A and B. And so I'm not going to do it that way. Now, what I'm going to do is I'm going to do it the way I would normally teach you, to avoid sign errors. And the only reason it works just like I've shown you, that's fine. If you have your own way of doing it, that's totally okay. This is to get you some techniques that have seemed to work for me really well. So what I'm going to do is I'm going to rewrite this as negative x squared plus 1. I'm going to factor that negative. I'm going to factor this right now so that I see the linear factor so I'm not screwed up on something like a trig sub or something weird. And now when we see this as a separable differential equation, we can group our x's, dx's, and our negative 1 dt. So I'm going to move my x's to the left-hand side. On the right-hand side, we just get negative 1 dt. And when we see our integral right here, when we see this, on the left-hand side, you have to be seeing these partial fractions. You go, yep, there's nothing I can do with that. That is why I put this in order. That's why I factored it appropriately. So I'm seeing two linear factors. I'm seeing I can separate this fraction into two different fractions. Two factors, two fractions. Both linears, constant numerators. So I'm going to do that. Why I chose to put this in this order, factor the negative, is because I see a lot of sign errors happen if I don't do that. Again, it's not a huge deal, but it's a deal. So let's try to separate this by partial fractions. We know that two factors means we're going to get two fractions. Linear factors means that we're going to get constant numerators. Now we're finding the common denominator. So 1 would equal a times x plus 1 plus b times x minus 1. And what that gives us, it says if you found common denominators, your numerators would have to be equal. So we're going to take that, we're going to run with it. We're going to say, hey, what if x was 1? Notice how 0 doesn't help us, but if x was 1, this would be 0, this would be 1 plus 1, this would still be 1. So we'd have 1 would equal a times 1 plus 1 plus 0. If x is 1, this whole term would be 0. So a would therefore be 1/2. Now, if x were negative 1, this would be 0, this would be negative 2. So this term is 0, this would be b times negative 2, and b would equal negative 1/2. So that allows us to split up that fraction and say, all right, well, if a is 1/2 and b is negative 1/2, then this fraction becomes two different fractions. 1 over 2 times x minus 1 minus, because b is a negative, minus 1 over 2 times x plus 1. And this is all dx. Equals integral of -1 dt. So a couple other things. What might you do? Well, personally, I'd probably factor out the 1/2. I'd probably multiply both sides, honestly, before I even did anything. I'd probably factor out that 1/2. Also, if you don't want to deal with this negative, you can factor in a -1/2. I'm going to show you that right now, just to show you some things that we can do. So if I factor out a -1/2, then this would be -1 over x minus 1 plus 1 over x plus 1. Notice I'm factoring out a -1/2. You distribute, you get positive 1/2, -1/2. If we multiply both sides by -2, then this would give us an integral of 2 dt, or 2 times integral of dt. So we've avoided a fraction, we've avoided a 2. We won't have any 1/2 ln's. That's kind of nice to deal with that. On the right-hand side, that would, no matter what way you do, by the way, so if you didn't see that, it's fine. I'm just showing you some small techniques here. Then this would still work out to 2 dt. Imagine that. If you had a 1/2 and a 1/2, you did your integration, you have a 1/2 ln, a 1/2 ln, you multiply by 2 anyhow, and that would still be a 2t. What's c sub 1? C sub 1, because we know we're going to be dealing with some logarithms. We're dealing with logarithms, means we're going to have an exponential. We're going to be changing that arbitrary constant. So on the left-hand side, we'll have no need for a u sub at a basic u sub, but no need for any coefficient changes. We'll have a negative ln absolute value of x minus 1 plus ln absolute value x plus 1. And we talked about just a minute ago how when you have logarithms added together with the same base or subtracted, we can make this one logarithm with the positive or plus on the numerator and the minus or negative on the denominator. Now we're ready to take both sides as an exponent on e. So we do it, we go, all right, e to the both sides here. On the left-hand side, and we're going to do a couple things because we literally just did it. We're going to have x plus 1 over x minus 1. On the right-hand side, you know that you'll have e to the 2t times e to the c sub 1, and we're going to put the absolute value equals plus and minus that. And we'll call all of that our arbitrary constant. So x plus 1 over x minus 1 equals arbitrary constant c, e to the 2t. Should you solve for x right now? No. Also, I made a comment a little while ago that I really want to try to set these up so that my denominator has a single term. Well, I couldn't do that. Both of these fractions had 2 terms in them, so it really didn't matter about our negative. I just factored a negative because I didn't want that one to be negative. I wanted to deal with an exponential with a positive exponent. That's the only reason why we did it. Could you have got here without doing what I did, without changing this around? Could you have just factored this? Yes. If you see that that's factorable as a difference of squares, great, do it. If you see that that's factorable as difference of squares and it still leads you to partial fractions, that's great. Okay, you're totally fine to do that. I've just seen a lot of students get really jacked up about this and be like, oh, that's not partial fraction, I don't see. So I've learned that if I write this in order, make them factor and negative, they'll see difference of squares better, they'll see linear factors better, they won't get messed up with negatives, sign errors won't happen, the A's and the B's are much more consistently found that way. And then I will get the correct coefficients out of them. Because imagine this, imagine if you screwed up that sign. This whole thing is smoked. Okay, your problem is done. So that's why I've done that. Huge deal? No, not a huge deal. But I've also said, well, I want that to be positive. So notice I'm factoring a negative. I wouldn't have had to do this if I didn't set this up this way. So I factor the negative. It's basically undoing what I've just done. And then I want a positive exponent on my exponential, so I've got that. That looks really good because we had to change that at the very end of the last problem, if you remember. E on both sides there. I've wrapped up my arbitrary constant as a giant C, and right now is where you'd want to plug in that initial value. So we're going to plug in x equals 3 when t equals 0. That's really nice to do right here, because if I plug in t equals 0, this is 1, and if x is 3, we get 3 plus 1 over 3 minus 1 equals c. That's 2. So 4 over 3 minus 1, that would be, man, just 2. That's pretty nice. Let's rewrite it. So we'll have x plus 1 over x minus 1 equals 2e to the positive 2t. And now it's just about solving for x. So here's what's going to happen when we have more than one term on the denominator. We are going to multiply both sides by the denominator, but we're going to have to distribute, collect our x terms on one side, non-x terms on the other side, factor our x, and divide. So I'm going to be multiplying both sides by x minus 1. I'm going to be distributing. We're going to group our x terms on the left, our non-x terms on the right. With a lot of negatives floating around. We're going to factor our x. And now since we group our x terms, we can factor the x, and now we divide. So x as a function of t equals negative 1 minus 2e to the positive 2t over 1 minus 2e to the positive 2t. That's a lot of negatives. One thing that we could do, if that's not looking that great to you, you could factor out a negative from your denominator or numerator and distribute it through the opposite. So I'm going to factor a negative out of this. What that's going to do is that's going to create this this negative 2e to the 2t minus 1. Yep, that would work. And then I'll run that through the numerator. So I'll distribute that on the numerator. And our function can look quite a bit different here. We could get positive 2e to the 2t plus 1 over 2e to the 2t minus 1. That might look a lot nicer for you. A little bit easier to plug numbers in, kind of see what's going on with that. So if your problem is not looking exactly the same, you have a lot of negatives, sometimes it's nice to do. I hope it's making sense. I hope that you're seeing some of the nuance of appropriately working with partial fractions. Again, these things are optional that I'm doing. I don't want you to say, well, I've done it different my whole life. That's fine, guys. I'm just showing you the way that I do it because it works really well for a lot of people. So we have one more, and I will be right back with it. Okay, so here we go. Last one on just a recap of how partial fractions work, especially in differential equations. Now, I could give you just the integral of partial fractions as just link a video, and I can do that too if you want. But in setting these up, there's some things that we want to deal with first before setting up to do our integral with partial fractions. It comes stemming from these differential equations. Number one is recognize them. So we have a differential equation. We have two linear factors already. It's already factored for you. I would say I'm going to change that, but they're already kind of setting this up as something that is going to be done with partial fractions. So if we're seeing separable. Hopefully you're seeing they're separable. You can get our x's, dx's, constants, dt. But what I want to notice is that might screw up some signs for us. So I'm going to change that real quick. What I'm going to do is I'm going to factor a negative and write this in what I would say a slightly better order. Now, does it really make a difference moving forward? It doesn't make a difference, but for the students I've helped, it seems to make a lot of sense. We're going to group our x's dx and our constants dt, and we are ready to integrate. It's just that since we wrote this as two linear factors, and since we saw that this is separable, now we have 1 over that. Well, that right there shows us that that's going to be a partial fraction. Partial fraction decomposition. So when we set this up as linear, when we set this up as something recognizable, when we group our x's dx, it's going to be more apparent if you take care of some work beforehand. So now we're going, yes, that's for sure partial fraction. No crazy trig subs or anything weird. Now we say, all right, let's separate this fraction. We know that there are 2 factors, so that's going to give us 2 fractions. We know that they're both linear, so our numerators have to be constants, 1 degree below that. We know that in order to do partial fraction decomposition, all we're really doing is finding a common denominator and setting our numerators equal. So if we were to find a common denominator, it would be a times x minus 5, and it would be b times x, and that would have to equal the numerator of 1. Then we also further understand that we can plug in some numbers like 0, and if that's 0, then 1 would equal, so 1 would change, a times negative 5. And a would equal negative 1/5. That's kind of nice. If x was 5, then this whole term would be 0, and 1 would equal b times 5. Or b would equal 1/5. Now we've seen this very similar problem before. So when we break this up, when we decompose this into some partial fractions here, then we're going to have this integral changes to, well, let's see, a is negative 1/5. So that would be negative 1/5 x plus b is 1/5. Do not distribute that. 1/5 times x minus 5 dx. And then on the right-hand side, we get this negative 3 dt. Now, the reason why I said don't distribute that, those both have a factor of 1/5, and we're going to factor that out. Also, I told you this, and for me, this is great. This looks really good because my single term, the denominator with the single term has a negative in front of it. So think about what's going to happen. We're going to factor a 1/5, right? We'd multiply both sides by 5. That'd be fine. It's going to be 15 over there. On the left-hand side, I'm going to get 2 logarithms. One of them is negative, and that logarithm that's negative is going to have a single term inside, x. That's great, because when I put this together as a fraction, I'd have 2 terms over 1 term. That's a simple multiply, combine, or collect some terms with the x in it, and then factor and divide. That's easy. What I'm going to do is show you how to do it if you're not practicing that method. So I'm going to do something a little bit different. I'm going to factor out a negative 1/5. I'm going to show you how to deal with an ln when you have 2 terms on the denominator, how you'll need to multiply, distribute, collect, factor, and then redivide. So I'm doing this on purpose, even though this looks really good to me. I would keep it this way. All I would normally do is factor a 1/5 like this and say, hey, this would be negative 1 over x. This would be plus 1 over x minus 5. That'd be fine. What I'm going to do is I'm going to factor a negative to show you what happens when you have 2 terms on the denominator. So negative 1/5 would create a positive 1 over x minus a 1 over x minus 5. Let's verify that. Multiplying, you get negative, and you get positive this. Now, what is kind of nice is that when I multiply both sides by negative 5, at least I'm not going to have to deal with a negative exponent that I'm going to get when I take both sides as an exponential on that e. Either way, we would have been fine, though. On the left-hand side, we're going to get ln absolute value of x. We're going to get minus ln absolute value of x minus 5. No problem. We should be very comfortable with that. On the right-hand side, we get a 15t plus c sub 1. We know that we're going to be changing that c sub 1. Now, let's combine these. And you're going to see what I'm talking about right now. I said that when you have a subtraction and 2 terms on your denominator, eventually that's going to become your denominator when you combine these into a single logarithm by the quotient rule. On the right-hand side, that 15t plus c sub 1, that still looks fine. right here, we're saying, hey, we've done this 3 times in a row now. Let's take both sides as exponents on that exponential function. On the left-hand side, we just get x over x minus 5. On the right-hand side, we're going to get plus or minus e to the c sub 1 times e to the 15t. And this is what we're going to call that c. So let's move up here and do a little bit more work on it. Let's double check. Looks pretty good to me. What do I do now? What I don't do now, I don't solve for x. Right now, I use my initial value after you've redefined your constant, that exponential raised to that constant. After you've done that, now's a real good time to plug in that initial value problem, or the initial condition, initial population. We're dealing with population problems. So 0 for t, 8 for x. And since we're plugging in 0 for t, 15 times 0 is 0, e to the 0 is 1, that's awesome. That means c is 8/3. And let's rewrite it. So since c is just this constant 8/3, we know x over x minus 5 equals 8/3 e to the 15t. Now, this is what I was talking about. We are going to have to multiply by that denominator, but now that denominator has 2 terms. So we're going to have to multiply by x minus 5. We're going to have to distribute that. We're going to have to get our x's on one side, constants on non-x's on the other side, so stuff with t's in it, factor, and then divide. It's just one extra step, but it is an extra step. So had we not factored the negative, we wouldn't have to do that. We would have multiplied by x. Our exponent would have been negative, though. And so, well, I guess maybe you consider that too. I think that's easier to deal with, but you consider that as a step 2. So either way you go. What I am going to do, I am going to multiply both sides by 3 though, because I don't like that fraction. So if we multiply both sides by 3, we get a 3x over x minus 5 equals 8 e to the 15t. That is nicer. Now let's multiply both sides by x minus 5. And we're forced to distribute. We have to do that. So when we distribute this, we're going to have a 3x equals 8x e to the 15t minus 40 e to the 15t. And now what we're going to do, we're going to group our x's on one side. And we're going to factor that x out. And then we're going to divide. So when we factor that x, let's see, 3 minus 8 e to the 15t equals negative 40 e to the 15t. And dividing, we have a function of x in terms of t that's negative 40 e to the 15t all over 3 minus 8 e to the 15t. Now, what do you think you'd do? Do you think you'd leave like that? Do you think you'd deal with a negative? Most people would say you're going to deal with a negative right here. You're going to take this negative in front of the 40 and distribute through your denominator and change a couple signs with that. So this should really look like 40 e to the 15t over positive 8 e to the 15t minus 3. Please do not simplify the 40 with the 8. Please don't simplify the e to the 15t over e to the 15t. You can't do that stuff, not unless you can factor, and we can't factor anything here. So I hope that's made sense. I hope that this has refreshed your memory on not just partial fractions, but how to deal with them in differential equations, that we're really looking to make some factors first. That way, when we put this as a separable differential equation and separate our variables, that's more easy to see that it's a partial fraction. I hope I've made the case on why you might want to, not necessary, but why you might want to have a denominator with a single term. It's just a little bit easier to deal with in a lot of cases. So other than that, what we're going to do next time is I'm going to take these ideas that we've done, and since we're really, really good at these partial fractions now, we're going to apply them to some population models and see how they work. So I'll see you for the next video on that. I hope you've been enjoying this exploration of some more real life examples with population stuff. We're going to get back to that in the next video. Have a great day.